The Pacific Ring of Fire represents one of Earth's most dynamic geological features, serving as a powerful reminder of the planet's active interior and the ongoing processes that continue to shape our world's surface. The Pacific Ring of Fire is a horseshoe-shaped zone of intense geological activity that encircles the Pacific Ocean basin. This region is characterized by frequent earthquakes, volcanic eruptions, and active mountain building processes, making it one of the most seismically and volcanically active areas on Earth. The Ring of Fire stretches approximately 40,000 kilometers, 25,000 miles, and encompasses the coasts of several countries including Japan, Indonesia, the Philippines, New Zealand, Chile, Peru, the western United States, Canada, Russia, and many Pacific Island nations. It forms an almost complete circle around the Pacific Ocean, though it's more accurately described as a horseshoe shape since it doesn't extend across the entire northern Pacific. The Ring of Fire exists because of plate tectonics. The Pacific Plate, along with several smaller plates, interacts with surrounding continental and oceanic plates through three main types of boundaries: subduction zones, where oceanic plates dive beneath other plates, transform faults, where plates slide past each other, and spreading ridges, where plates move apart. Most of the Ring of Fire's activity occurs at subduction zones, where the denser oceanic plates sink beneath lighter continental plates, creating intense pressure and heat. About 75% of the world's active and dormant volcanoes are located along the Ring of Fire. This includes some of the most famous and dangerous volcanoes such as Mount Fuji in Japan, Mount St. Helens in Washington state, Krakatoa in Indonesia, and the Andes volcanic chain in South America. The subduction process creates magma as the descending plate melts, leading to explosive volcanic eruptions that can have global impacts on climate and air travel. Approximately 90% of the world's earthquakes occur along the Ring of Fire, including about 81% of the world's largest earthquakes. The constant movement and collision of tectonic plates creates enormous stress that is periodically released as seismic activity. Some of the most devastating earthquakes in recorded history have occurred here, including the 2011 Tohoku earthquake and tsunami in Japan, the 2004 Indian Ocean earthquake and tsunami, and the 1960 Chilean earthquake. Approximately 90% of the world's earthquakes occur along the Ring of Fire, including about 81% of the world's largest earthquakes. The constant movement and collision of tectonic plates creates enormous stress that is periodically released as seismic activity. Some of the most devastating earthquakes in recorded history have occurred here, including the 2011 Tohoku earthquake and tsunami in Japan, the 2004 Indian Ocean earthquake and tsunami, and the 1960 Chilean earthquake. Countries around the Ring of Fire have developed sophisticated monitoring systems using seismographs, GPS networks, satellite imagery, and ocean buoy systems to detect and track geological activity. While scientists can identify areas of increased risk and monitor ongoing volcanic activity, precise prediction of major earthquakes and eruptions remains challenging. Early warning systems for tsunamis have been established throughout the Pacific to provide coastal communities with crucial evacuation time. The Ring of Fire wasn't always configured as it appears today. Its current form developed over millions of years as the Pacific Plate, which is the largest tectonic plate on Earth, gradually shrank due to subduction along its margins. During the Mesozoic era, roughly 250 to 65 million years ago, the Pacific was much larger, but continuous subduction has been consuming its edges. This process created the ring pattern we see today, with volcanic arcs and earthquake zones marking where the Pacific Plate meets other plates. Several significant subduction zones define the Ring of Fire's most active segments. The Cascadia subduction zone along the Pacific northwest coast of North America is capable of producing magnitude 9+ earthquakes and has a history of generating massive tsunamis. The Japan Trench System, where the Pacific Plate subducts beneath the North American and Eurasian plates, created the devastating 2011 Tohoku disaster. The Peru-Chile Trench along South America's west coast is the longest subduction zone on Earth and has produced some of the largest earthquakes ever recorded, including the 1960 Chilean earthquake with a magnitude of 9.5. The Ring of Fire contains numerous volcanic island arcs formed by subduction processes. The Japanese archipelago, the Aleutian Islands of Alaska, the Indonesian island chains, the Philippines, and New Zealand all represent classic examples of island arc volcanism. These islands exist because subduction creates magma that rises through the overlying plate, eventually breaking through the ocean floor to form volcanic islands. Over geological time, these volcanic processes have built entire island nations. A notable feature within the Ring of Fire is the andesite line, which roughly corresponds to the ring's boundaries and separates two distinct types of volcanic rock. Inside the ring, in the Pacific Basin, volcanic rocks are predominantly basaltic, while outside the ring, andesitic and more silica-rich volcanic rocks dominate. This chemical difference reflects the different volcanic processes occurring in ocean basins versus at convergent plate boundaries. Different segments of the Ring of Fire exhibit unique characteristics. The Indonesian segment is particularly complex, involving multiple plate interactions and hosting some of the world's most explosive volcanoes, including Tambora and Krakatoa, whose eruptions have had global climatic impacts. The Andes mountain chain represents the world's longest continental volcanic arc, with over 180 potentially active volcanoes. The Kamchatka Peninsula in Russia contains one of the highest concentrations of active volcanoes in the world, with over 30 active volcanic systems. The Ring of Fire includes some of Earth's deepest ocean features. The Mariana Trench, located in the western Pacific, reaches depths of over 11,000 meters, 36,000 feet, below sea level, making it the deepest known point on Earth's surface. These trenches form where oceanic plates bend downward as they begin their descent into the mantle during subduction. The intense geological activity along the Ring of Fire creates numerous hydrothermal features both on land and underwater. Terrestrial examples include the geysers and hot springs of Yellowstone. Though Yellowstone itself is caused by a hotspot rather than Ring of Fire activity, the geothermal features of New Zealand, and the volcanic hot springs throughout Japan. Underwater hydrothermal vents along the Ring of Fire support unique ecosystems that thrive in the absence of sunlight, relying instead on chemosynthesis. Despite the hazards, the Ring of Fire regions are often densely populated and economically important. The geological processes that create risks also provide benefits. Volcanic soils are extremely fertile, supporting agriculture in countries like Indonesia and parts of Central America. Geothermal energy from Ring of Fire volcanism provides significant power generation in countries like Iceland, New Zealand, the Philippines, and parts of the western United States. Additionally, the tectonic processes concentrate valuable mineral deposits, making many Ring of Fire regions important for mining. The 21st century has witnessed several catastrophic Ring of Fire events that demonstrate its ongoing activity. Beyond the well-known 2004 Indian Ocean tsunami and 2011 Japanese tsunami, other significant events include the 2010 Chilean earthquake, numerous Indonesian volcanic eruptions and earthquakes, the 2014 eruption of Mount Ontake in Japan, and the ongoing volcanic activity in the Philippines, including recent eruptions of Taal volcano. Major volcanic eruptions along the Ring of Fire can significantly impact global climate patterns. The 1815 eruption of Mount Tambora in Indonesia caused the year without a summer in 1816, leading to crop failures and famine across the northern hemisphere. More recently, the 1991 eruption of Mount Pinatubo in the Philippines temporarily cooled global temperatures by about 0.5 degrees Celsius due to the sulfur dioxide it injected into the stratosphere. Scientists expect the Ring of Fire to remain highly active for millions of years to come, as the fundamental tectonic processes driving its activity show no signs of slowing. Climate change may influence some aspects of Ring of Fire activity, particularly through sea level changes that could affect coastal volcanic systems and through altered precipitation patterns that might influence volcanic hazards like lahars, volcanic mudflows. Understanding and preparing for Ring of Fire hazards remains crucial for the billions of people living within its influence. The Ring of Fire's volcanic activity varies dramatically in style and intensity based on magma composition and gas content. Subduction zone volcanoes typically produce andesitic to dacitic magmas, which are more silica-rich and gas-rich than oceanic basalts. This creates highly explosive eruptions characterized by pyroclastic flows, ash plumes, and volcanic bombs. The dissolved water and gases in these magmas, derived from the subducting oceanic plate, act like a shaken soda bottle when pressure decreases, leading to violent explosive eruptions. In contrast, some Ring of Fire volcanoes, particularly those in more oceanic settings, produce less explosive basaltic eruptions with characteristic lava flows. Ring of Fire eruptions often trigger cascading hazards that extend far beyond the immediate volcanic area. Pyroclastic flows can travel at speeds exceeding 100 km per hour and reach temperatures of 1000 degrees Celsius, devastating everything in their path. Volcanic ash can disrupt air travel across entire continents, as demonstrated by the 2010 Eyjafjallajökull eruption in Iceland, which grounded European air traffic for weeks. Lahars, volcanic mudflows, form when volcanic material mixes with water from rainfall, melted snow, or crater lakes, creating concrete-like flows that can travel hundreds of kilometers from their source and remain hazardous for hours or days. The Ring of Fire's earthquake activity demonstrates the complex ways seismic energy travels through Earth's interior. P waves, primary waves, and S waves, secondary waves, from Ring of Fire earthquakes provide scientists with crucial information about Earth's internal structure. The shadow zones created when seismic waves encounter Earth's liquid outer core were first identified through analysis of Ring of Fire earthquakes. These seismic studies have revealed the layered structure of our planet and helped scientists understand mantle convection patterns that drive plate tectonics. Large Ring of Fire eruptions can trigger volcanic winters through stratospheric injection of sulfur compounds and ash. The 1815 Tambora eruption created sulfuric acid aerosols that reflected sunlight back to space, causing global temperature drops that persisted for several years. These events can disrupt monsoon patterns, affect crop yields worldwide, and even influence historical events. The 1783 to 1784 Laki eruption in Iceland, though not technically part of the Ring of Fire, demonstrates how volcanic emissions can cause widespread famine and may have contributed to social unrest preceding the French Revolution. Ring of Fire earthquakes generate tsunamis through various mechanisms beyond simple seafloor displacement. Submarine landslides triggered by earthquakes can create tsunamis, as can volcanic eruptions that displace large volumes of water. The 1883 Krakatoa eruption generated tsunamis over 40 meters high through explosive collapse of the volcanic island. Pyroclastic flows entering the ocean can also create tsunamis, while caldera collapse during major eruptions represents another tsunami generation mechanism unique to volcanic regions. Recent research suggests that Ring of Fire activity may be connected to deep mantle processes occurring thousands of kilometers below the surface. Some scientists propose that subducted oceanic plates can penetrate all the way to the core mantle boundary, potentially influencing mantle plume formation and deep Earth dynamics. The Ring of Fire pattern may reflect these deep connections, with subducted material affecting convection patterns that ultimately influence surface volcanism and seismicity. Ring of Fire volcanoes are major contributors to atmospheric chemistry through their gas emissions. Beyond the well-known carbon dioxide and sulfur dioxide, these volcanoes emit hydrogen sulfide, hydrogen fluoride, and numerous trace gases that can have regional environmental impacts. Some Ring of Fire volcanic areas experience VOG, volcanic smog, that creates air quality issues for local populations. The halogen gases emitted by these volcanoes can also contribute to ozone depletion in the stratosphere. The intense heat and pressure associated with Ring of Fire subduction zones create extensive metamorphic rock formations and hydrothermal systems. These processes concentrate economically important minerals including gold, silver, copper, and rare earth elements. The Kuriko-type massive sulfide deposits found throughout the Ring of Fire represent some of the world's most important mineral resources, formed by hydrothermal processes associated with submarine volcanism. Scientists studying Ring of Fire hazards increasingly rely on paleoseismic evidence to understand long-term patterns of activity. Tree ring studies, sediment cores, and archaeological evidence reveal patterns of major earthquakes and tsunamis extending back thousands of years. For example, studies of ghost forests along the Pacific Northwest coast provide evidence of massive Cascadia subduction zone earthquakes that occurred approximately every 300 to 600 years over the past 10,000 years. Modern Ring of Fire monitoring incorporates increasingly sophisticated technologies. GPS networks can detect millimeter-scale ground movements that precede major earthquakes, while satellite radar interferometry (INSAR) can measure volcanic ground deformation from space. Ocean bottom seismometers provide real-time earthquake detection in previously unmonitored offshore areas, while infrasound monitoring can detect volcanic explosions from thousands of kilometers away. Machine learning algorithms now analyze patterns in seismic data that might escape human detection. Life around the Ring of Fire has evolved remarkable adaptations to extreme geological conditions. Deep-sea hydrothermal vent communities rely on chemosynthetic bacteria that derive energy from volcanic emissions rather than sunlight. Some terrestrial plants have evolved tolerance to volcanic soils high in toxic metals, while certain animals show behavioral adaptations to predict seismic activity. These biological systems provide insights into how life might exist in extreme environments on other planets. Ring of fire volcanism has profoundly influenced human cultures, religions, and mythologies throughout history. Many Pacific cultures developed sophisticated traditional knowledge systems for predicting volcanic activity and earthquakes. Japanese Shinto traditions incorporate volcano worship, while Pacific Island cultures often view volcanoes as dwelling places of gods. These cultural connections continue to influence modern disaster preparedness and risk communication strategies. Many of the world's largest megacities lie within the Ring of Fire, creating unprecedented concentrations of vulnerability. Tokyo, Jakarta, Manila, Los Angeles, and Santiago all face significant seismic and volcanic risks while supporting millions of inhabitants and critical infrastructure. The interaction between natural hazards and urban systems creates complex risk scenarios that require innovative approaches to disaster preparedness, building design, and emergency response planning. Thanks for watching. Like and subscribe, and don't forget to explore more geological wonders on our channel.